Hello, I'm Chris Athanas. I'm a KMP developer, and today we're going to continue our series, How to Program from the Ground Up, and we're going to get into the back to object oriented programming, my favorite. Oh yeah, heard from tech support. Yeah, unfortunately, the guy they trained up, he quit right after they trained him. He's going working for the competition now, which is that company that it went under and got restructured. They're starting up another spinoff, so he's going to go work for them. So hopefully they'll have their staffing situation put together soon, so we'll get that portal closed and off my to-do list. All right, let's get into enough of the silliness. Let's get into the meat of this thing. So back to object-oriented programming. This is what I call it because there's two. There's the COP style OOP. There's two styles of OOP. There's the COP style OOP, and then there's this style OOP, which is really the original one. Even though this kind of existed before, but they just never called it this thing until this guy came along. And Mr. Kopp, Bjorn, he took the term and co-opted it. It should have just stuck with C with classes. C with classes actually described what his stuff does. Way better than C++, which is just computer speaky computer language for increment one. Ooh, okay. It's so funny. It must be so much better then, right? Okay. All right. So the big idea. Oh wait, I refresh this. I just changed this. Let me get this thing over here. Put this thing over here. Okay. Can we revisit the original principles of OOP, which is what this guy was talking about, to make software easier to understand and maintain? So the big idea. The state of the program is immutable and only changeable by creating a totally new state and by modifying the old state. That's why we talked about the function stuff, because this is one of the big ideas, okay? And the state of the objects is private and only mutable via methods of that class that are called on the object. So you have to ask nicely. You can't just jump behind the counter and start making the sandwiches just because it's quicker. If you're going to try, okay, that's not scalable. That's not scalable. It means that every single person now has to know how to make sandwiches. So what are we doing? Okay, yes, you can jump behind the counter and make the sandwiches way faster. But, okay, so we have to have some layers of abstraction. Are you going to have people work on the mechanics of the car too? And yes, that's kind of the idea. We're going to be mechanics. We're going to be sandwich makers. We're going to be chefs. We're going to be bankers. We're going to be politicians. We're going to do all the roles all at the same time. Yeah, it's going to be real efficient. Right, you'll be able to do all that stuff exactly the way you want, but you're gonna run around all day. That's the idea. You're running around in your mind with this stuff, and you kind of just want to extract that stuff away, so you're not running around in your mind so much, because it gets very tiring. Alan K style OOP, the original OOP. I called it Boop. I call it back to OOP, but I didn't want to call it Oopie. I thought Boop was a pretty fun name. It also stands for the Boogie Professor's Boogie style. This is where I got this stuff from. I haven't completely done his pure style, so I've had to make some changes, which I have documented and have a couple projects showing off. One in Java, a couple in Kotlin. One is a back end in Kotlin. One is a front end KMP. So it's in this style. So listen to what Alan Kay said in '97. We was already quite frustrated with the things in the direction that had been taken in the last few years. So let's hear what he has to say. So we're gonna watch videos, right? The reason why we're watching videos, you can jump ahead and look at the code if you want to. You have to understand the philosophy, because it is a different way of thinking about the problems. You're not grabbing behind the counter. You're having to structure things so their messages are being passed. Yes, it's less efficient. Yes. But the bottleneck is not the masking of the message anymore. The processing of stuff, it's going to be the part of the system. But the message passing is not critical anymore. So, and it is truly messages, because these objects of these classes have to be asked nicely, and they can refuse, and they can tell you why, and not just grab it. And they can also change their internal implementation, and you still ask nicely. They might have a restructuring of their staff, they might have a staff restructuring, but you don't have to know about all that stuff. Well, in case of this, because I'm intimately detailed oriented with the portal. But in general, you don't want to know about staff changes. You just want to send your order in and get your pizza out. You just want to, you don't want to know how the thing's cooked. If it's a truck or grandma's or somebody's hand patting the thing, you You just get the order and put it how they want to do it. It's up to them. That's the idea. So let's listen to Alan Kay talk about this. So by the way, I'm only going to do snippets of these things and make comments. You need to go listen to all of his stuff. If you're going to go down this route, you have to listen to like why is he doing it like this? And there's a whole layers of this thing that there's a reasoning behind this that allows for easily readable code with domain-driven design. If you're using the domain names in your code, whatever domain you're in, and this, it can just reduce your cognitive load tremendously and also get rid of a whole class of bugs. Let's listen.
OOP work, or any kind of programming work, is that there has to be some exquisite blend between beauty and practicality. There's no reason to sacrifice either one of those, and people who are willing to sacrifice either one of those, I don't think really get what computing is all about.
Okay, so that's what he's talking about. So he's talking about the efficiency of going in and grabbing, like the cop thing does, or you have this other style, which is like we're trying to elevate we're trying to create some abstractions here that make sense, right? And we're not overwhelmed with complexity. And that's what he's talking about here. And I apologize for the quality, but these teachers, this is what you get. They were not promoted. They were not jacked up. They were not shown this is like, and their technology was a little ahead of the time, but now it's arrived and we can use it and we don't have to argue about it. We can still use the cop stuff where it's appropriate, and we use this stuff generally we're doing programming because it's way easier to understand what's going on. There we go.
It's like saying I have really great ideas for paintings, but I'm just going to use a brush but no paint. So my ideas will be represented by the gestures I make over the paper. And don't tell any 20th century artists that, or they might decide to make a videotape of them doing that and put it in a museum. So I thought I had this problem figuring out what to talk about.
I think that was a Jackson Pollock stab, which turns out it was a CIA operation. But anyway, let's keep going.
It's always difficult because technical people always seem to know so much. But it's interesting to look at what's actually being done out in the world under the name of OOP. And I've been shown some very, very strange looking pieces of code over the years by various people, including people in universities, that they have said is OOP code and written in an OOP language. And actually I made up the term object-oriented. And I can tell you I did not have C++ in mind.
Now, here, this is what we're talking about. So he's coming out swinging. He's coming out swinging.
So the important thing here is I have many of the same feelings about it. And I can tell you I did not have C++ in mind.
I didn't do anything. I don't know. Just want to hear that again. Okay, whatever.
So the important thing here is I have many of the same feelings about Smalltalk, and I'm going to try and I'm not going to try and do Smalltalk in here because I think there's one really important thing about Smalltalk and some of the languages like it that we should pay really, really close attention to. But it has almost nothing to do with either the syntax or the accumulated superclass library, both of these are taken as being the language, as though it was issued from some gods on Olympus. So I want to
like the C++ libraries are, and all the other libraries you ever encounter. It's like, this is the one way to do it. And the developers oftentimes, because they're young time, a lot of times they're young, or a lot of times they just like one thing over another. And it's like, this is the way to do it. It's like, no, that's just a way to do it. It's a way to do it. It's not the way to do it. And it will change within 6 months because there's always a better way. Come on now.
I'll talk a little bit more about my personal reaction to OOP when I started thinking about it in the 60s. And instead of making it a historical talk, to try and think about whether these reactions and insights have any place today. So I'll just move. So I guess my slide thing doesn't work. There's a sense of simple mechanism, because computers, of course, were as large as this room. The one that Ivan Sutherland did Sketchpad on was the size of this room. It was one of the last computers in the US large enough to have its own roof.
Oh, we'll get into that. I don't think he shows it here, but we'll get into what that was.
It was the building it was in. But the programs were quite small, and they had a lot in common with their mathematical antecedents. And one way of thinking about the semantics of math that is based on logic is as interlocking gears. Everything kind of has to fit together, and if it does, and everything's compatible at the end, you get the the final turning of the shaft that you want. And sort of a real-world analogy. Go to the next slide, please. Whoops. So we missed a slide. Go back 2 slides, please. There we go. So an analogy to these programs of the 60s is a doghouse. You take any random boards, nail and hammer, pound them together, and you've got a structure that will stay up. You don't have to know anything except how to pound a nail to do that. Now,
so when we first start learning programming, we're just building doghouses. It's really hard to get hurt in those. And everything, you can see everything. You walk around, look at all the pieces. You can look inside, see everything, how it's all built. It's movable. You can break it apart real easy, put it back together, no problem. I love doghouses. They're super great to learn about what you want to do. And you can build doghouses for all kinds of things, right? You can do a chicken house or a cat house, or you're going to it's a small thing, right? That's the point here.
Somebody could come along and look at this doghouse and say, wow, if we could just expand that by a factor of 100, we could make ourselves a cathedral. It's about 3 feet high. That would give us something 30 stories high.
Makes sense, right? Just double it, triple it. That's fine.
And that would be really impressive. We could get a lot of people in there. And so the carpenters would set to work blowing this thing up by a factor of 100. Now, we all know, being engineers and scientists, that when you blow something up by a factor of 100, its mass goes up by a factor of 1,000,000. And its strength, which is mostly due to cross-sections of things, only goes up by a factor of 10,000. So when you blow something up by a factor of 100, it gets about a factor of 100 weaker in its ability. And in fact, what will happen to this doghouse, it will just collapse into a pile of rubble. And then there are 2 choices you can have when that happens. The most popular one is to say, well, that was what we were trying to do all along.
And that's called a death march project. That's called keeping going with bad ideas and not knowing when to start over and throw things away, to bite the bullet. No, we got to ship this quarter. No, we got to ship this quarter. No, we got to ship this quarter. But we have this thing that's taking 5 times longer because now we're at 2 months because we could do it in 2 days. If it takes 2 months, no, we got to ship this quarter. That's a lot of these dang projects. It's crazy. So I'm like, get in your head like, hey, there might be another way to approach these problems that isn't so nuts.
Put more garbage on it, plaster it over with limestone, and say, yes, we were really trying to do pyramids, not Gothic cathedrals.
Facades and adapters and all this. So there's these patterns, C++, trying to like get away from some of the crazy details that are exposed.
That, in fact, I think accounts for much of the structure of modern operating systems today.
I would say that's true. He was dogging out Windows and Mac. Mac at the time, it was starting to fall apart, guys. And you had this thing all this whole time. You didn't try and make it like, no, it was working fine. Like, okay.
Or you can come up with a new concept, which the people who started getting interested in complex structures many years ago did. They called it architecture. Literally.
Don't say that word. Don't know it's a dirty word.
The designing and building of successful arches. A non-obvious, non-linear interaction between simple materials to give you non-obvious synergies and a vast multiplication of materials. It's quite remarkable to people when I tell them that the amount of material in Chartres Cathedral, which is an enormous physical structure, is less than the amount of material that was put into the Parthenon. And the reason is it's almost all air and almost all glass. Everything is cunningly organized in a beautiful structure to make the whole have much more integrity than any of its parts. So that's the other way you can go. And part of the message of OOP was that as complexity starts becoming more and more important, architecture is always going to dominate material. And in fact, the sad...
So it doesn't matter. You're eventually going to have to deal with the complexity thing. You're going to have to deal with it. You can only go up so far before it's like, okay, you have to now do with it, because then it starts to go to rubble every time, right? And that's what we're talking about.
Fact, I think, about OOP is people didn't get interested in architecture because of the beauty of it. They're only starting to get interested in architecture now when the internet is forcing everybody to do it. That's pretty pathetic.
Kind of pathetic. Because he's talking about academia here, and he's also talking about the industry as well, because of how they promoted this C++ to everybody and how it's supposed to solve these things. And it's object-oriented. Yeah, it's object-oriented, and it's not. And that's why Alan Kay is he's still salty. And I'm salty about it. We missed out. There's a whole... the thing hasn't started yet. We're still on the front of this computer revolution.
So I'm going to use a metaphor here for this talk, which is drawn from a wonderful book called The Act of Creation by Arthur Koestler. Koestler was a novelist who became a cognitive scientist in his later years. And one of the great books he wrote was about what might creativity be, learning. He realized that learning, of course, is an act of creation itself because something happens in you.
Learning is an act of creation. This is what we're doing, really.
That wasn't there before. Learning, of course, is an act of creation itself because something happens in you that wasn't there before. And using the metaphor of thoughts as ants crawling on a plane. In this case, it's a pink plane. And there's a lot of things you can do.
This is the COP plane. People thinking I'm doing OOP. This is a COP plane. It's just almost the same line as the C. So it's like we're on this flat plane. Like okay, we don't think we're doing stuff. Okay.
On a pink plane, you can have goals. You can choose directions. You can move along, but you're basically always in the pink context.
It's just like normal incremental thought patterns about how to see the current set of problems. That's all he's talking about.
If you think about that, it means that progress in a fixed context is almost always a form of optimization.
Like just making that thing, just like, can we make it better, this thing? Not really changing how we're approaching anything. Can we just make this thing better? Can we make this loop faster? Can we do this algorithm? It's like, no, we're not trying to look up at see the problem context bigger. We're just looking inside the cognitive context. Can we get 5 saws on the log and do can we do that kind of level of things? So just one saw, we get 5 saws. Okay, yeah, maybe, but that does that scale?
Because if you were actually coming up with something new, it wouldn't have been part of the rules or the context for what the pink plane is all about. So creative acts generally are ones that don't stay in the same context that they're in. So he says every once in a while, even though you've been taught carefully by parents and by school for many years, you have a blue idea. Maybe when you're taking a shower, maybe when you're out jogging, maybe when you're resting in an unguarded moment, suddenly that thing that you were puzzling about, wondering about, looking at, appears to you in a completely different light, as though it were something else. And Koestler said the emotional reaction to this comes basically in 3 forms, which is if you're telling a joke, it's ha-ha. If you're doing science, it's aha. And if you're doing art, it's ah.
So he's talking about these human qualities of like, seeing it from a different perspective and then trying it out and going, oh, wait a second, there's something here, right? And it wasn't there before. Or it was kind of there, but not, it was like all the pieces were there. But like someone actually going along saying, what about this and not that? And then going, ooh, well, this puts you over here. I was like, oh, this is interesting. That's what he's talking about.
He says, because in each case, something very similar is happening. A joke takes you down the garden path and then suddenly reveals it's about something else, and you get a very aggressive explosion. And science has much of the same feeling to it, and often when you see something in science, you start laughing because it was right there in front of you, and it is a kind of a joke.
Right, it was kind of a joke because it was there the whole time. All you had to do was twist your brain around a little bit, and you could see this other thing that was there. It is like that.
Of course, art is there to remind us, great art is there to remind us that whatever context we think we're in, there are other contexts. Art is always there to take us out of the context that we're in and make us aware of other contexts. So this is a very simple, you could even call it a simple-minded metaphor, but it will certainly serve for this talk today. And he also pointed out that you have to have something blue to have blue thoughts with.
So the blue is like the new, kind of like how we put this together.
And I think this is generally missed in people who specialize to the extent of anything else. When you specialize, you're basically putting yourself into a mental state where optimization is pretty much all you can do.
We have a banking system. It needs to be done this quarter. How was it done before? How did that bank over there do it? Okay, do it like that. And only change it a little bit, change the names here and there, but just do it like that, okay? That's different. That's optimization, right? How can we make this thing go faster and faster? We can take over that job of that bank and that job of that bank, and etc.
You have to learn lots of different kinds of things in order to have the start of these other contexts. So here's a couple of knocks on the head I had over the years. I just want to tell them to you quickly. This one I think you'll find interesting because it is the earliest known form of what we call data abstraction. It goes all the way back, actually pre-1961. I was in the Air Force in 1961, and I saw it in 1961, and it probably goes back 1 year before. And so back then they didn't really have operating systems. They had, Air Training Command had to send tapes of many kinds of records around from Air Force Base to Air Force Base. And there's a question of how could you deal with all of these things that used to be card images, and then because tape had come in, were starting to be more and more complicated formats. And somebody, almost certainly an enlisted man, because officers didn't program back then, came up with
which you lowly. They're so lofty. They're above that.
And came up with the following idea. This person said, on the third part of the record on this tape, we'll put all of the records of this particular type. The second part, the middle part, we'll put all of the procedures that know how to deal with the formats on this
the functions
third part of the tape. And in the first part, we'll put pointers into the procedures. And in fact, let's make the first 10 or so pointers standard, like reading and writing fields and trying to print, and let's have a standard vocabulary for the first 10 of these, and then we can have idiosyncratic ones.
1961, by the way.
Later on, and so all you had to do to read a tape back in 1961 was to read the front part of a record, one of these big records, into core storage, and start jumping in direct through the.
Right, so to keep the programs, the machine language code be in the language, so you would bring the code in right when the program was being loaded. That's pretty clever.
Pointers and the procedures were there. Now, I really would like you to contrast that with what you have to do with HTML on the internet.
Yeah.
Think about it. HTML on the internet has gone back to the dark ages because it presupposes that there should be a browser that should understand its formats. This has to be one of the worst ideas since MS-DOS.
It definitely puts a closed system around things, for sure.
This is really a shame. It's maybe what happens when physicists decide to play with computers.
He's super pissed. He's so pissed about it. It's so funny to watch him just be like, these guys that we think are just these gods. It's like, hey, there's another thing going on, yo.
This is really a shame. It's maybe what happens when physicists decide to play with computers. I'm not sure. And in fact, we can see what's happening to the internet now is it's gradually getting, there are two wars going on. There's a set of browser wars which are 100% irrelevant. They're basically an attempt either at demonstrating a non-understanding of how to build complex systems, or a even cruder attempt simply to gather territory, which I suspect Microsoft is in the latter.
And that's what it is. Come on now.
Camp here.
We all know that now.
You don't need a browser. If you followed what this staff sergeant in the Air Force knew how to do in 1961. You just read it in. It should travel with all the things that it needs. And you don't need anything more complex than something like X Windows, hopefully better. But basically, you want to be able to distribute all the knowledge of all of these things are there. And in fact,
and when I first started computers, that's how it was. You had these little tapes, and you load them up, and everything would be in there that you need to do on the thing. And that's this idea. So that's an object. The tape with the pointers and the data and the programs on it, that's an object.
The internet is starting to move in that direction as people discover ever more complex HTML formats, ever more intractable. So this is one of these mistakes that has been recapitulated every generation. And it's just simply not the way to do it. So here's a great idea. And by the way, this kind of programming was done before there were higher level languages in the Air Force. And this approach to things was forced out of the Air Force by COBOL when they standardized on COBOL. Ivan Sutherland.
Okay, so we're going to look at this Ivan Sutherland. Very important to know what this is about. Is it right here?
Okay, so.
Oh, let me find it. Hold on. All right, he's talking about this thing.
About in the early 60s, the experimental computer for the.
These are all tubes. These are all tubes. This is inside the computer for tracking all the incoming missiles and stuff like that, if in case of a nuclear attack. This is what this thing does. And they all have them on these racks, and they can pull out these racks. These are all tubes. Floors and floors filled with these tubes, all being air conditioned up to the ceiling and the floor. It's crazy. Yeah, they did. And of course, you got a little smoking ashtray because you're going to be in there a while, swapping out tubes all day long.
Stage project, which was called the TX2, was enormous. It was the size of the building, and sort of was the building. And we learned to think about this as the time when there was only one personal computer. And that was when Ivan Sutherland got to use it from 3 o'clock in the morning to 6 o'clock in the morning because Wes Clark liked him. And here's what he did. This oscilloscope could only plot points, so he first had to write software to actually make it into a display. He had to invent rubber band lining. And then he did something wonderful. He allowed you to just sketch something and then tell the system what you wanted it to be. In this case, he said all of those lines had to be mutually perpendicular. You just saw the first clipping window ever done. And here he wants to make a hole in this flange. So he points to those and says, I want them to be parallel and connected to the top guy. And he's using them here as guidelines to make these dashes. So the constraint here is collinearity. And then
you see a little mistake there? This is crazy that he was doing this. This guy was super. Ivan Sutherland, he was just amazing. He started the whole flight simulator. It wasn't for this guy, with the whole flight simulator thing would have been taken off like it did. This guy was amazing.
He makes the guidelines transparent, and lo and behold, we have dashed lines. So he's made a hole in the flange. Now he wants to make a rivet to put in that hole. So he got some more ink.
The app's called Ink.
And just sketches out the idea of a rivet. He's going to use this cross point here as the center for the arc for the top of the rivet. And again, he's going to tell the program to make these lines mutually perpendicular, and you are seeing Sketchpad solving that problem in real time. So he gets a nice symmetrical rivet. This is all done in 1962 with one guy in 1 year on this huge computer. Here's another solution to that problem. Now, he could have constrained the ratios of the lines to each other. But here, what he's doing is just saying, okay, just solve this problem, and what's close to it will give me a nice rivet. And of course, you want more than one rivet. So what he's actually working on here is what was called a master drawing. In today's terminology, we would call it a class of a rivet. And here's an instance of a rivet. You can see he's can continuously change the scaling and rotation. Those are done by knobs on the console. And here he's making more instances of that rivet. And you realize, oh, wait a minute, I don't want that crossbar, so I'll make them transparent on the master drawing, and that means all the instances will also reflect that. So we think of that as part of what we call object-oriented programming today. So this was an object-oriented system, and I think the first real one ever done. And anything you make in the master drawing, you can make instances of. So here he's making instances of the flange with a rivet in it. And
So it's like a new class extends that particular implementation of that class. That's pretty. This was like early stuff, and we lost it along the way.
Capture that as a master, and so he can get instances of those and scale and rotate them as he wishes. And in fact, all of the alphanumeric information.
You're starting to see it bog down as it gets to flickering here. You're starting to see the limitations of this display technology.
The display was also done this way by just drawing them into the system. So here's a close-up of the console, and you see Ivan sitting at it with a light pen in his hand, and on the screen we see something that looks like a truss bridge. And unfortunately, there isn't a movie available of this, so we did a recreation of kind of how this truss bridge worked in Sketchpad. So here's the console. We zoom in, and as before, we can construct the truss bridge by just...
So this is a simulation of that computer running that software. It's crazy. We have this now. We didn't have this for the longest time.
And now we've turned on gravity, which is trying to make the masses go to the bottom of the screen, and you see the stresses and strains on these beams here being expressed, and you see them change
numbers
as we put weights on them. This made me think of what we were doing at NCAR with trying to simulate the weather, that what we really wanted was something that was interactive, real-time model of the universe that we're interested in, that would allow us to try out different situations. So I think of this as the real birth of computer-aided design, but not just CAD, but also SIM. And
so that was kind of like some of the thoughts that were hanging around at the time. Let me get the next one queued up. Okay, yeah, this is the right one.
Right? Because that's all there is. That is the background color. And if we go up in that world, we don't know it's pink.
So we're kind of continuing this conversation from before we did the little interlude and showed the Ivan Sutherland machine he was talking about. And now he's talking about the pink and blue lands. The pink is the horizontal one where everything's optimized, and the blue is like you're trying some other thing that we haven't seen yet.
Right? Because that's all there is. That is the background color. It's the thing we are least interested in because it's the most constant thing. But every once in a while, you might have a little blue thought. Could be waking up in the morning, taking a shower. But remember, we grew up in this world. We went to church. We have parents going to school. Pink. Pink is what the reality is. But every once in a while, you get a kerpow. That kerpow is out of that world. It's actually an escape from that world. And in the old days, when people had one of these, they would start a new religion. Because how many people have had a kerpow?
Oh, yeah.
Like, the technical word for a kerpow is holy shit. How many people have had it? Come on. How many people have had holy shit? Holy shit. Where does it come from? So the subjective sense we have is we didn't have that thought. Something put that thought into our head. It just happened. So of course, if you don't have science and you're not wired to check out the kerpows, it seems to come from the heavens. Okay, so we dip into another world. This world, let's call it a blue world, blue plane world. And there are three things here. This explains why we have trouble making progress.
Yeah. If pink is the reality, like we should know all the design patterns, use every single one of them, and all of our code bases all at the same time. Stacks are a really good idea. In every case, because we have to make it go as fast as possible. So if this is reality, right? How those sane people think this it looks like. Okay.
If we treat our beliefs as reality, then how sane is blue? The answer is, well, it's not sane. Sanity is relative to the things we believe are true. So the first thing is you've immediately turned yourself into a crackpot for a few nanoseconds, and that's one of the fists that comes down and squashes you
Whoops.
back out into the pink world. I don't want to be crazy. Second one is when you're trying to explain this idea to somebody else, they really have to go through a similar process. This is probably the most difficult thing about an age of invention like the one that we live in. Invention is actually relatively easy with the right kind of funding. So the problem is getting something, is essentially pulling other people into a blue world, given that the blue world isn't really completely nutty. And then the third idea is that the blue plane is also a gully. So they have a half-life. So each one of these things, salvation! 20 years later, it's the albatross around your neck.
Yeah, the adoption curve there. It'll solve all our problems. Oh my God, there might be something wrong with this. We have to live with this for a while. Okay, there has a use case, but.
Right, and so anytime a company does something successful, and you can talk to corporate executives about it, they really think it's like they invented something really important. No, in fact, they
Marketing team, go. Conference team, go. Book team, go. Go, go. Sell, sell.
just found a heuristic that's working for a while, and if they forget to re-examine that heuristic, they're going to be in the same plight once again.
But we got to make some sales this quarter, dang it. The company's going to go under.
So this is a real picture. It's not. The sign says, do not touch any of these wires.
There's your C++ code with your statics all being looked at, and your public variables and everything just available anytime you want it. Just plug it in here. We don't care. It's fine. Nobody's paying attention anyway. But don't touch any of these wires.
And it's important to realize that every single one of these wires was a solution to a perceived problem. There's no other reason why it was done. It was done over a period of time. This is related to this idea. Anybody can make a doghouse. You can make it out of almost anything, matchsticks even. You can make it out of cardboard. You can make it.
I think we talked about that. Let's see if they're here.
So now it's about 150 feet high. It's tiny compared to the Superdome, but that doghouse will just fall in on itself. Completely. Has no structural integrity. And the reason is that when you double a solid, the mass goes up by a factor of 8. And the strength in simple materials like wood and beams and stuff has to do with the area. It's like the strength in our muscles. This is why gymnasts are small. They're small because they can have relatively large muscles, they have short muscle arms, and they weigh quite a bit less. That's why a grasshopper can jump 100 times its own length and we can't. They have the same kind of muscle fibers as we do.
But the C++ guy said we could make this grasshopper size of an elephant and it'll be fine. We could jump over buildings then.
And so the scaling thing takes what is a very nice idea for a dog and one you can have in 2 seconds and hit it together into something that you really do not want to carry into any kind of larger scales because there's no connection to the scaling. And if we come back to what we can do without special knowledge, we wind up with an Egyptian pyramid. It's the only big thing you can build without knowing how to build, which is just a big garbage dump and plastered over with limestone, so it looks good. But if you think about it,
I mean, not exactly, but okay.
it has no room inside.
I mean, some are, most of them are, but some aren't.
So in order to get the Superdome, you have to do that other thing. You have to go back to a different conception of what the materials are, which are actually tensile structures. And then you can build enormous domed structures that scale very, very well. So if we come back to this tangle, I just put software in here. It could be anything. The result of incremental problem solving.
We won't plan anything. We'll just build it up. We'll just build it a piece at a time. We'll design it as we go. The design is going to be emergent this year.
So this research community I came out of, Advanced Research Projects Agency in the 60s, and then Xerox PARC, which was an outgrowth of it. Basically, it was a bunch of small number of people who had big ideas who did not have big resources. They didn't want to give up their ideas, and so they were faced with this dilemma, is that they could not handle, they wanted to build a network that would go over the entire world. It was called the Intergalactic Network, back before it was called the Internet. And they could not
Interesting choice of words, by the way.
use any technique that Bell Telephone, AT&T used, because it didn't scale. Just completely out of the scope. And finally, in the 60s, one of the organizing insights was, hey, computers are virtualizers. That's what universal Turing machine means. What that means is, forget about wires. You don't need.
Right, you don't have to wire everything together. Same with a microprocessor. Before that, everything was hardwired computers. Microprocessors, we can just virtualize all that. You can still hook everything up, but we'll use this little thing in the middle to transfer what goes here, what goes there, what goes this. That's what he's talking about. That's all he's talking about.
No stinking wires. What we need to do is to forget about wires. You don't need no stinking wires. What we need to do is to understand how to organize systems as virtual entities, and we can render some of them in hardware and we'll render some of them in software. But in fact, everything winds up being something like a single communications line with an arbitrary number of entities on it. Everyone can talk to everyone else. And
so you're on a bus. Everybody's on a bus. That's all he's talking about here. And it is better to be on a bus than everything directly connected together as such.
Communications line with an arbitrary number of entities on it. Everyone can talk to everyone else, and all of a sudden you've thrown away all the things that Bell Telephone had and every piece of the way most software was done and replaced it with a simple messaging system.
And that's eventually what a lot of these things come into, is just sending messages back and forth. These big back-end computer, mega hardware, what is it called? What do they call them? The microservices. Ugh. It's just a bunch of little computers sending messages to each other using these object-oriented kind of ideas. There we go.
All of a sudden, a few people could do amazing things. So this is an example. I'll bring this up again a couple of times, but basically you need to solve the context. You need to solve the Grand Canyon problem. Most people are rewarded in school for solving problems. When was the last time your child or you were rewarded for finding a problem?
Yeah, not really thing.
You found a new problem, we've got too many already. Right? Whereas in fact, finding what the real problem is the big deal. And people will fight you every step of the way.
Absolutely. As they should, because a lot of new ideas are pretty dumb.
They'll fight your kids in school every step of the way if they're a problem finder type. Don't let the teachers hurt them.
That's true.
Most problems are bogus because they come out of the current context. We're trying to get beyond the current context. So forget about problem solving. It's just a bad heuristic. It's the last thing you do. And so you get these leaps. So here's a leap out of the context of the 20th century, mid-20th century, which is a gear kind of thing. Everything is closely articulated. The interfaces are very tightly bound, et cetera, et cetera.
Fragile. You change something, it's going to break.
The problem is you can only make a thing with about 1,000 gears.
C++, C++ fragile.
Gears in it before it seizes up. You just, et cetera, et cetera. The problem is you can only make a thing with about 1,000 gears in it before it seizes up. You just can't get the tolerances good enough. Does that sound like software?
Sounds like C++ kind of software, for sure.
Can't do it. But when you go to biology, we have 100 trillion cells in our body. Each and every body in here has about 100 trillion cells. Okay, I'm going to ask the audience.
Do that, like most of it's not even our most stuff that makes up our body is even a human DNA. Yeah, it's pretty wild. You can look up that up.
It's a question. You haven't asked me one yet. But the question I'll ask is, who knows how many of these 100 trillion cells in our body have our DNA in them?
Oh, that's right. He does talk about it.
Okay, predominant answer is all of them. Anybody else got an opinion?
Yeah.
So it turns out only 10% of them.
10%. I always forget that number. I think they even it's even lower than that. He's just being generous, not to be shocking to you.
Only 10 trillion of those 100 trillion cells have our DNA. The other 90 trillion, 9/10 of the cells in our body are slime. And that slime has people have been counting the species of microorganisms. You know, bacteria, E. coli is one of them. That should have been a clue. E. coli has its own DNA, which is very different from ours. So last count, I went on the internet the other night to see, was getting close to 25,000 different species of microorganisms, most of which we have no idea what they're doing inside of us. And they're about 1/2000th the size of our regular cells, so the 90 trillion cells of slime is about a basketball size of stuff all over us everywhere. That ought to make you feel better about lunch. But the point is, nobody's come close to building anything with 100 trillion parts or a trillion parts without, the only things we know that actually work with that many parts are biological things. Something to think about. And that gave us researchers back then a kind of a unified vision. Everything, this is a self-portrait of the internet after we built it. But this is the image. Hey, everything is like this. This is a biological model. We can't scale and have central control. Big problem with companies. They start off like families with a head.
Can't scale and have central control. You can't scale and have central control. Sorry. You have to pick one. Or slide it. You're going to slide it one way or the other. You just never can't. You can't have both. Sorry.
Head of the family. Try and get bigger. This is why monarchies are tough. Right? No way. You have to find a way of distributing control and distributing responsibility in an equal.
Well, it depends on the monarchy, so we're not going to get in that debate.
Logical way. This is not things that human beings like to think about. People are uncomfortable. Who's running the show? People say. Well, the answer is the internet does not have any center, and it's grown by almost 10 orders of magnitude now without ever breaking. Your software breaks all the time. The internet has never broken. It's replaced all of its atoms and all its bits at least twice since it started in 1969. It has never been taken down for maintenance.
Just like every person does every 7 years.
Think about that. Your software could be like that. The software we did at Xerox PARC was like that. Your software could be just running eternally. And so everything, at the expense of going to something more complicated than a data structure or some wires, everything can be built out of a single kind of entity that has functionality inside, it provides services on the outside, and there's something like a cell boundary on it.
She's talking about an object that has publicly exposed methods and then private data inside that it doesn't share with anybody else unless you ask nicely. Don't grab my stuff because I might change some things. They might not be there, so don't grab my stuff. But you can ask nicely.
It's worthwhile thinking about that. So if we come to PARC, here are a couple of things we did. Personal.
Okay, I don't want to go into that. You can go into that more detail. How many minutes? I got 40 minutes. Okay, but what are we doing now with this one? This one. This one. This one. This one. Okay, let's do a few minutes on this.
So Francis Bacon, here's Thoreau again. One of the advantages of reading a lot is hardly.
So he's talking about the limitations of our brains, right? We're talking about Francis Bacon, who was Shakespeare, probably the same guy. We don't know, but he was a big originator of the language and talked about, and a lot of his stuff talks about these limitations, these human foibles and limitations that we have, and how can we accept that we have these, not deny that we have these, and work with it somehow to make things better. Let's talk. Let's see what Francis has to say.
So here's Thoreau again. One of the advantages of reading a lot is hardly any of us, certainly me, all my ideas are derivative. Just because I've read thousands of books. I didn't have to puzzle this out because Bacon wrote a book called the Novum Organum in 1620 where he said, hey, look, our brains are messed up. We have bad brains. He called the ways of messing up idols. So we get serious errors because of our genetics. We get serious errors because of the culture we're in. We get serious errors because of the languages we use. They don't represent what's actually out there. We get serious errors from the way academia hangs on to bad ideas and teaches them over again. These are his 4 idols. Anybody ever
Optimize because you're past the test, right?
So we get serious errors because of our genetics. We get serious errors because of the culture we're in. We get serious errors because of the languages we use. They don't represent what's actually out there. We get serious errors from the way academia hangs on to bad ideas and teaches them over again. These are his 4 idols. Anybody ever read Bacon? He said we need something to get around our bad brains. A set of heuristics is the term we'd use today. And what he called for was what he called for science, because that's what Novum Organum, the rest of the title, was a new way of dealing with knowledge. And science is not the knowledge, right? Because the knowledge is.
Science is not the knowledge. Science is the process to acquire knowledge. Knowledge might change because science is the process of we finding out stuff. And science doesn't have to be done by scientists. Scientists it's really asking We're supposed to do it ourselves. We're supposed to be doing our science ourselves. We're supposed to be looking into this stuff. But work to death, and I get it. You don't have time for all that stuff. I understand. But that's just the whole idea of the Western culture is you're supposed to kind of elevate yourself to the point and be a participant in this whole mystery. We're trying to figure all this stuff out to make it a little easier for everybody involved. No? Never heard of it? Okay.
Is in this context. What science is a negotiation between what's out there and what we can represent. This is the big idea. This is the idea they don't teach in school. This is the idea we should be teaching. It's one of the biggest ideas of all time. It isn't the knowledge, it's the relationship, because what's out there is only knowable by phenomena that is being filtered in every possible way. And we don't know whether our brain is even capable of representing the stuff. And so to think about science as the truth is completely wrong. It's not the right way to look at it. But if you think about it as a negotiation between the best you can do right now and stuff that's out there where you're not completely sure, you're in a very strong position. Science has been the most powerful thought system human beings have ever invented.
One of them for some particular pushes for elevating masses out of poverty and out of sickness and out of disease and out of misery and labor. Yeah, it's been pretty good. But for other things, to be said, but been pretty good.
Because it gave up the idea of truth. And it substituted for it 1,000 variations of false, some of which are incredibly powerful. Right? This is the big idea. So if we're going to think about computing, this is one way. Now Seymour Papert thought about it in a different way, but this is one way of thinking about, wow, computers, they are representers. We can learn about representations. We can simulate ideas. We get a very good, much better sense of dealing with thinking about these complexities. Okay, so maybe one last part of this pep talk, and then I'll turn it over to Vishal. So let's go back to the pink plane here. And we're at A to B. Okay, so we can explore, we can tinker away around it, that's better. If that was good, we can engineer a superhighway. And if we're really adventurous, we can invent the airplane. Forget about land travel. Let's just fly over that mountain. And here's the big idea. Once we decide to take off from land travel, we not only are in a different world, we discover we're in a blue world, and the blue world has a much better destination than B. So I submit this as a metaphor that can be used in many different areas. Like, simple one, often you have to go away from your goal to get to your goal. That is a toughie.
Often you have to go away from your goal to get to your goal.
And what does that mean? That means...
This is the early 80s when he still had a lot of pep in his stuff. He still wasn't really mad yet.
Data structure, language. And it occurred to me and other people who were thinking about these ideas back then, what if you didn't do that? What if the only subdivision you ever made in a programming language was a subdivision of a computer into a computer? You were never allowed to subdivide the computer into something that was less than a computer. And what does that mean? That means that each subdivision has to be something like a black box that has inside of it some mixture of state and process. From the outside, you can only invoke behavioral attributes rather than invoking method attributes. And what I mean by that...
So what he's saying is, you're not just calling functions on these things. You're actually like, these are little, you could be better to conceptualize this as the individual units that will respond to a set of messages, and it gets to decide. However that happens, not your concern.
This is something that was even in Fortran, because the early designers of Fortran realized that there was a very funny correspondence between procedural things and data structure things. So for instance, when you say sin parenthesis 30 close parenthesis in Fortran, you can't tell by looking at that whether you're invoking a function or whether you're accessing an array. And that was not accidental back then, because of course they thought of arrays as being a kind of a function, and they wanted you to be able to write
a lookup table, a map. Ooh.
Arrays, huge tables, still done today, in order to do functional evaluation very quickly.
So in the early Fortran, what he's saying is, instead of having it calculate every single time, which the computer's super slow, it's like really sluggish. Back in that day when Fortran came out in the 60s or 50s, right? Instead of calculating each time, he just had a table that had a big array, a bunch of numbers already in memory somehow, usually magnetic tape or somewhere on some platter somewhere, or in core memory, they would code these things up, right? They would have the tables out to the precision that's good enough for what they were doing. And instead of calculating, it would just look it up, right? If it's sign 30, if it's sign 30.1, sign 30.2, it'd look it up. So all these lookup tables. So it would go a lot faster. So it wasn't doing a lot of calculation stuff, but it just look it up in the back of the, just like they had in the back of the day. they would have these books. They were just numbers. Okay, you want this number? This is the result. There's a logarithm. There's a sine. There's a cosine. It's like, we should just put this number in the computer. That's the big idea.
What they didn't realize is they wanted to be able to trade off between the two. But that notion of just saying sine 30 degrees without indicating how it's to be computed is the essence of the kind of abstraction that object-oriented programming is all about. It's carried very far here by...
Right. So you don't care whether the computer actually is calculating sine 30, or it's going looking it up, or someone's looking when the thing comes in and you're typing in, because you've got this genius over here who can do it way faster than the computer. So when he sees a number, he just types it in the computer. You don't care.
This strong membrane of the object, so that what we're dealing...
Strong membrane, meaning I have public methods. You can't come inside my private stuff. You can't see it. Strong membrane. That's what the metaphor is using.
with here are behaviors, and there are two important implications that had to be worked out early on. One of them is that messages, in most cases, can't be commands, or you're violating the notion of the object as being in control. Now, most object-oriented
The subtle difference.
systems today, when you do what is called sending a message, you are issuing a command.
Calling a function. Yes, C++, he's already kind of dogging on C++ right here, and that's not what he's talking about. He's actually has this other thing in mind.
Objectives.
But it looks like just calling a function, just they look the same. But how they're treated is very different.
C, C++, even Smalltalk 80,
Well,
all of those
not very different. How about just different?
systems, Objective-C, C++, even Smalltalk 80, all of those systems, a message is actually something very, very close to, if not identical to, a certain kind of procedure call. Okay, but in fact, in the original scheme, and we can talk about the implications of why this is a good idea later, in the original object-oriented systems that were so successful, messages aren't commands at all. What they are desires. I'd like to have this happen. Just to give you an example.
But please do this for me.
Of why. Imagine we have
Not you best do it or else. And I'm waiting.
an object masquerading as a critical system file. And the question is, should just anybody be able to come up and issue the command to it, turn byte 5 to 0? Now, it's done all of the time, but in fact, in an object-oriented system, you would like the object to be able to protect itself so that even a person who has a pointer to it, even a person who has the knowledge of which command is the right command, that both of those do not imply that you have permission to actually change that file.
So he's anthropomorphizing this thing, but really the idea is not that the object gives a crap. It's the programmers of the system say, hey, you can't just go into the thing and change this digit. You can't change the view count. You have to have proper authorization. I want to know your password. I want to know that you've been logged in properly. You're not changing. Somehow that little object is going to go check to see who you are. You said before I change the view count. You just can't say change view count or grab in there and just change the number. No, that's why we're doing it, so we can put reduce the complexity around what's going on. That's it.
So when I talk about an object-oriented system, I mean an object in which the worst you can do to an object is to simply indicate to it that you would like it to do something for you. And the best that can happen is it will do that. The worst that can happen to it internally is it will simply refuse. It may take your name and give it to the principal later if you've done something wrong. But so this notion of absolute control of messages can't be commands. And the other one is because the object is no longer a data structure in any sense that we regard it, that assignment is something that can't be done from the outside either. So the assignment statement has to go away in the form that we know it as an irrevocable change to a variable.
So he's talking about the public variables. You just can't go in there and change the variables. So he's just repeating the same. He's just repeating the same thing, just like I am.
A slot in a data structure. An assignment has to be changed by something that we can think of as being advice or influence. So again, this notion of getting an object to change its state is something that we normally don't do in object-oriented programming, because normally in object-oriented programming we're not simply trying to imitate data structures. Now, to me, a data structure is that thing that if you send it to somebody else, you're giving them permission to change it. That's what I mean.
Right. So that's C with classes. That's the cop style. You passing these things or these data structures around, and even though they're inside of an object, it's the same thing as inside of a file, and you're just calling a function out to do it. That's what he's saying. There's a different here. He's trying to get people to, in his language, to say, hey, there's two things here, and he didn't know enough at the time right here that he should say it's really different things. He was still trying to hold on to the OOP instead of just accepting loss and went to MOP, message-oriented programming. If you would have done that, if you would have accepted the L, and just said, we're talking about MOP. That's something else. You can call that OOP. That's fine. I'm talking about MOP. There we go.
By data structure. So it's clear that
So some of these guys are pretty stubborn, if you haven't noticed.
the things that we call data structures in normal parlance,
My word.
in a system with an operating system that offers some protection, are not strictly classical data structures by that means. Certain files usually have protections on them so that in a good operating system, when we send a file from us to somebody else, we are not conveying to that person the same level of protection necessarily that we have been granted. So in a good operating system, this may be an operating system that you've never seen, but there have been operating systems in the past, and there exist operating systems now, so that if you have a certain set of permissions.
So he's talking about still PC era when they had everything was open on a PC. Everything could be writable, readable. There's no permissions or anything. He's talking about like Unix, where you can set permissions, group permissions, if you're allowed to access a file or not. So that's all he's talking about there. Okay, so the next thing we're going to be getting up to is we're talking a little bit about objects versus statics here with Professor Bugayenko. And every time I hear Professor Bugayenko, this is what I hear. So it's Professor Bugayenko. Let's see, it's Professor Bugayenko. Okay, here we go. Okay, quit messing around. Listen to the professor.
And the agenda is that, first of all, I'll give a little bit about the theory, like why I think so. The second one, I'll give you a practical example of how I faced the problem with the static method in Java and how I resolved it myself in one of the open source frameworks I'm working on now. Then I will try to answer a few concerns people expressed on the blog in the comments, and I will try to give the answers to them.
So he's talking about static methods versus objects. So we're just killing about that delineation, like, are you allowed to just grab my stuff, or do you have to ask nicely?
And then I hope you will have some questions for me, and I'll be able to answer them. So let's start with the theory. Let me show you first. Let me share a piece of code with you, and I'll explain what the static method is about. So here's the code. The first piece of code, this one, is, well, you probably understand what it does. It's like it's a small class which compares to.
So this final means you can't extend it. This is going to be the only class. You're not allowed to extend it. That's all that means. And private, you understand. Public, you understand already. That's it.
To integers and returns the biggest of them. So the class is a pair, and this method returns the biggest value in the pair. It does this by the help of this, it's a Java code, by the help of this static method, it's a utility class, math, and there's a static method max in this utility class. So I think that this is wrong, and this is right. It's exactly, well, almost exactly the same class.
So this right here is calling a static method on this static. It's just a bunch of, it's a bag of utilities for doing math. And you're just passing these things in, and it'll just give you a static thing back. This is actually creating an object of this max thing that he'll explain, and then that only when you ask for this thing, this biggest, will it actually calculate it. Here we go.
But it also encapsulates two numbers, and it also returns the biggest of them. But it does it differently. It does it by the instantiation of an object, and then it returns an object. Instead of returning a scalar integer here, it returns an object of type of interface number, and this object is a maximum between, well, a maximum of these two numbers. So I believe that the first example, this one, is terribly wrong, and this is way better. It's not perfect.
Okay, so he's talking about Boop, his Boop style. He's got a little pure. He's a little more pure than me. He's got his own EO style, but it's close enough to Boop to talk about what we're talking about. This is a very trivial example. What we're talking about is a little bit more advanced stuff, and this is just so we can get the conceptual difference. This is the exercise we're doing right now.
The second one is not perfect because it still needs refactoring, but the first one is terribly wrong. So why is that? I think that static. Let's step back a little bit back to. Let's try to compare the procedural. This is procedural programming. This is object-oriented. This is more object-oriented, and this is procedural. Why is that? The procedural programming, it's the idea how the software looks in the procedural programming. The application is a long set of statements which are supposed to be executed one by one, starting from the entry point and finishing at the exit point of the software. This is how C.
Like every single example I've done in this whole series so far, it's been all procedural based. except until this next one I'm going to do, which will be the boop style.
Software is designed. You have the main function, and this main function gets control when receives control from the operating system, and then it goes statement by statement till the end.
Just like from the beginning, assembly language, basic, C. Well, C was a little different. You had to still have a main entry point with C. So C started to break away from it, but this is the idea.
If you write the long main function in C or in assembly or in basic, in all these procedural languages, you will end up with a very long function. We call it functional procedure. Basically, it's a procedure. So it's going to be very long listing, like multiple, many thousands of lines of code. In order to decompose this problem into smaller pieces, they invented procedures, which are basically pieces of code taken away from the main function.
Subroutines and functions, that's all we're talking about.
And placed somewhere else and labeled somehow. They call the procedures with the name and parameters. And then you may call them, and the execution will go there. They will continue there using the stack. So you pass the parameters into the sub-procedure. Then the execution will continue in the sub-procedure, and then will return back to the main procedure. So you can
function calls. Okay.
Break down the big scope of the problem into procedures and sub-procedures. But still, the entry point of the software is at one point, and then you go through all these statements one by one. You continue to execute till the software ends, till the end of the application. Or
you might do a loop. You might have a conditional. You might check the network. You might wait for the network to come back. But it's a thing all the way to the beginning of the end. Now, some programs like these desktop applications say loop. They wait until you hit Command Q, and then they're done. Same thing.
Script execution. This is how the procedural programming is actually. Let me stop this. You can see me again. So this is how the procedural programming is intended to decompose the problem into pieces. And that decomposition method actually has problems, and that's why object-oriented programming was invented. Because if you decompose that way, you will end up with a software which is very unmaintainable and difficult to extend and difficult to refactor or to add some features to fix the bug.
To modify, to understand, I'll have people to come in on onboard. Like, what is all this crazy stuff? Oh, that's this and this is that and that. Why is this being? Can I change this here? Am I allowed to change this here? Is something using this?
Because every time you're basically dealing with the scope is still big, and you're always managing the data, which goes through all these procedures deeper and deeper into smaller procedures. So basically, it was difficult to maintain this kind of software. That's why object-oriented programming was invented. In the object-oriented programming, to decompose the problem,
boop style
problem into pieces, you do it completely different. You break down, you present your whole software as a big one object, which is composed into which encapsulates smaller objects inside, and you wire these objects one to another, mostly through constructors, not through functions, not through method calls. So the entry point to the
we will do a demo. I'll show the code next thing. You can skip ahead, of course, but I'm gonna show you the code the next time. The next video.
Procedure to the entry point to the procedure is actually this function or procedure, which is the data which comes in and then the amount of statements. But with the object, the entry point of the object is a constructor. So in OOP, when you design the software, you break down the problem into smaller elements, which are objects, and then you wire them together through constructors. So you allow one big object to encapsulate multiple other objects, and these smaller objects also encapsulate smaller objects through constructors. So in OOP, the functions are small, really small, like a few lines of code, but the constructors are, the objects, they have more constructors and less functions. So the decomposition problem in procedural programming is different from decomposition in object-oriented programming.
Yes, it's a mind. You have to think. It's not huge. It's not like, oh my God, this is like the sky is green and the grass is blue. It's not like that. It's still like, oh, this is a different way of looking at things. Oh, okay.
That's the key difference. In the code which I've showed you just before, let me show it again.
But the way people treat this, the amount of static this guy's gotten from just talking about this, and Alan Kay from the C++ crowd, is crazy. Guys, we're just trying to make things easier for everyone. I know you might give up 2 horsepower on your cop car, but can we make it easier to get people on board, and we can add features to this beast and not break everything every 3 seconds? Please.
Yeah, in this code, when you use the static function, the existence of this function actually encourages you to turn this function also into a static function.
Right, and so why not? Why not make that static too? Who cares?
Remove these 2 things and put them here.
Yeah, that's faster, right? More efficient, right? But isn't that just the procedural again? No.
So that's where your software will get if you keep using static functions and you keep liking them and you keep appreciating them. So eventually, it's like a cancer in the object-oriented programming. It will eventually cover your entire code base.
Right. It brings you back to the procedural style. So you're losing all the benefits of OOP. Now you're just now you're adding complexity when it's not necessary. If you just want to do procedural, go back and just do procedural. It's most cases it's probably the way you should be doing it, or at least that part of the program is part of the application. You can make it procedural. But you try and mix these things together, you're just creating more work. Why are you making more work for yourself?
Eventually, all of your functions will be static because you will see no point in encapsulating anything because this is way faster. This is less lines of code.
It's right. It's faster to read. It's faster to write. It's faster to execute. It's actually everything is faster except to change it, which is all the stuff that we're doing all the time is changing this stuff. So we're trying to optimize for the changing of it, not the execution of it. Now, if it becomes a bottleneck, we can fix that. But in general, we're trying to do this other thing now because the problem that we're running into is we're building these doghouses and they're falling over. And everyone's mad and pointing fingers. You're a mad doghouse builder. You didn't build skyscraper doghouse the right way.
It's going to work faster, and it will look for you, if you think in procedural way, it will look for you like a perfect procedure from a C style, from the way you decompose the problem in procedural programming. So this will look like a perfect design for you, and then you will eventually turn your pair class into a utility class, which will have only static functions. And then everybody who actually is using this pair class will also think like, why do we need this to be a class? Why do we need to make an object of this class? We can just call this a static function. And then for me, if I'm a client of this function, of this object, sorry, of this class, then I also don't want
a user, someone that's instantiating and making it.
Want to have the proper object. I can use only static methods. So if you go that way, if you keep using static methods, public static methods, then your whole software, your entire object-oriented software, which will become not an object-oriented, but a software with a procedural decomposition. So you will actually get back to C programming in a Java syntax.
Worst of both worlds. Okay, so we are going to end it there. And we're going to get into some more examples next time. And yeah, Professor Bugayenko.